So the first speaker of this session is Sally Dodson-Robinson, who is an associate professor at the University of Delaware, and we will be hearing about her work on NWelch. So Sally, I will turn it over to you. I can see your slides and I can hear you just fine.
Okay, thank you. So NWelch actually grew out of my effort to understand another code that was written in Fortran. I have been working on techniques for sorting out planet detections from stellar activity, and I'd been reading a lot of the geophysics and paleoclimate literature and cross-spectral analysis. So when you analyze the power spectrum of the cross correlation of two time series, is a good way to reveal oscillations that are in common to two time series. So that's really helpful when you're studying exoplanets because if you find that your radial velocities in a Doppler survey and some kind of stellar activity indicator share an oscillation at a certain period, then that's a red flag. You know not to claim a planet detection at that period because that's going to be a stellar signal. Um, so I was trying to work with this Fortran code that I found in the geoscience community, and I realized that if I really wanted to understand the numerical method, I had to code it myself. So that's what I did, and then I realized that other people could use this code too once I passed it on to my students. So finally, I released it on GitHub. So the goals of NWelch are to detect oscillations in common to two time series, even if there's noise in both, and even, this is very important, if there's a phase shift between the oscillations. So if you have two oscillations with the same period, but they are out of phase, this technique will still work. And then the other thing that you get for free if you are looking for oscillations in common to two time series is you get a power spectrum estimate that has less variance than the Loam-Scargill periodogram. So on the bottom here, you see an expression showing that the Loam-Scargill estimator of the power spectrum of a data set is actually the variance of that estimator rather is proportional to the power squared. So, and there's no n number of observations on the right-hand side of the equation. So you can add yourself as, millions of data points and you can't get that variance down. So we would like to have statistical methods that do better than that, that can actually um, be asymptotically lowering our variance, okay? So addressing science goal one, which is to detect oscillations in common to two time series, this is just a toy model that I have. So on the right, I have in the upper right plot, I have two time series. The x of t is supposed to simulate a stellar activity indicator, so it could be H alpha or it could be calcium H and K, and it has a rotation signal. So that's x of t here, and then there's also noise added. And then y of t has the rotation signal, and it also has a planet signal. That's what you see in red, and that's supposed to represent your radial velocities. And so they both share the rotation, which has a rotation frequency of, oops, of 1/25th of a cycle per day, so a period of 25 days. But then the planet period appears only in the red, the simulated RVs, and that's got a period of 80 days. So one common method for looking for these shared signals is to simply plot your radial velocities as a function of your activity indicator. So that's the middle plot, y of t of x of t. Y of t is a function of x of t. And if you do that for this data set, you get just a mess. So if you look at this middle plot on the right, it looks like, oh, there's absolutely no relationship between y of t and x of t. So you conclude that stellar activity is not manifesting in your data set, in your radial velocities, but that's untrue. You can see that very easily if you calculate a cross correlation between the two fake time series, which you see on the bottom right here. So the shared oscillation is very obvious in the cross correlation. So that's great, but we have a problem when we are observing from the ground, which is that our data sets are unevenly spaced. So you can just see a couple of radial velocity time series here for a couple of M dwarfs. And what you'll notice is that the time intervals between the observations are uneven. Whereas this toy model I generated with just a delta t of 1 day. So in this case, when you have unevenly spaced time series, you can't calculate a cross correlation directly, but you can go into the frequency domain and you can calculate a frequency dependent correlation coefficient. So the Fourier transform of your cross correlation, which is on the left of this equation here, is also equal to the product of your conjugated Fourier transform of x of t times your Fourier transform of y of t. So as long as you can compute a non-uniform fast Fourier transform, then you can get the information that's contained in the cross correlation about those oscillations. And then, so there's more information that you can get. So on the right here, this equation on the top left is just the same as the equation on the previous slide, but you can actually see what the complex valued cross spectrum of those two time series from the previous slide look like. So we have the real part and the imaginary part. And sure enough, you can see the shared oscillation. And then one thing you can do is you can take that complex valued cross spectrum and you can normalize it by the product of the periodograms of both time series. And that's this middle plot, and that's called magnitude squared coherence. And since this is symmetric about zero frequency, we only plot the positive frequencies, but you can here see a hugely significant signal at the shared oscillation, so this 25-day rotation period that I put in my data. And a key thing about this coherence estimate is that you have to actually average together multiple estimates of both the cross spectrum and the periodograms, the power spectra, in order to calculate it, which means the denominator here of this middle equation gives you your lower variance power spectrum estimates for free. So goal 2 comes for free if you look for if you can do goal 1. And then finally, you can also get a phase spectrum. And on the bottom right here, I've plotted the phase spectrum. And at the rotation frequency, the phase difference between the two signals is 270 degrees, which makes sense because one of them is a cosine, the other is a sine. Um, so how do you get your multiple estimates that are required for this middle equation here for your coherence? Well, you have to break your data into segments. And so this is just what it looks like to do that. This is one way of segmenting your data set. And so you compute power spectrum and cross spectrum estimates from each individual segment, and then you average together those estimates. And you can make your segments overlapping, and I highly recommend doing that wherever possible because it gets you more data points per segment, which means that your power spectrum estimates are better, more robust. However, it's not always possible to overlap because we've got giant gaps from the seasons in our astronomical time series. So let's go to some science results. So this is GJ 581. Um, at one point, I think there were maybe 6 planets that were reported to orbit this particular star, but now we're down to 3. Two of them in particular made a big splash because they were, um, supposedly Earth mass, possibly Earth-like planets. But those got refuted, and so you can see the kind of warning in this top plot here. So these are power spectrum estimates. And the observable that is in this time series from which we estimated the power spectrum is the H alpha activity index. So in the light blue is the Lohm-Scargill periodogram. In the dark blue is our low variance power spectrum estimate from Welch's method, which is why the software is called NWelch. And you can see on the left, the leftmost vertical line shows the rotation period. It's detected way above the 0.1% significant false alarm threshold. And then also the harmonics of that rotation period are also detected at high significance. Well, it turns out if you go down to the RVs, you just follow these vertical lines downward. The two refuted planets were actually detected at the harmonic frequencies. So it doesn't look significant in this periodogram because we haven't subtracted out the planets with the highest RV amplitude. So you can see way over to the right of this bottom plot in the RV power spectrum estimates, there's a peak, and that's planet B. And then there's another peak around 0.076 frequency. That's another planet. Um, but these peaks didn't manifest until you subtracted out the orbits of those higher amplitude signals. Um, However, they are stellar activity. They are not planets, so they're rotation harmonics. And that's very obvious in the Welch's power spectrum estimate of the activity indicators. It's not at all obvious in the Loam-Scargill periodogram. And then if you look at the magnitude squared coherence, so this is the same thing that I showed you on my plot with the toy data set, except the vertical axis is different. So this is a variance stabilizing transformation. Um, and so basically anything above this red line is very significant. So that's a 0.1% false alarm probability. And the solid is analytical false alarm thresholds, and then the dotted are bootstrap. And so we find that they agree very well, the analytical with the bootstrap. Um, and what you'll notice is that, first of all the dotted lines are rotation harmonics, and you'll see huge signals within a resolution element of the rotation harmonic. So this is a complex rotation signal, as you might expect from an M dwarf. And second, the planets D and G that are really not planets, if you look at the gold, which is just the bandwidth of this estimate, you can see big signals in our coherence between H alpha and RV. So definitely above the 1% false alarm threshold. So the planet frequencies show up in this coherence between activity and RV. So this is a really useful metric to detect oscillations in common to two time series. And one thing that we've learned from this work, because we've worked with other M dwarfs, is that you have to really beware because their rotation signals are complex and you can get quite a lot of high order harmonics. And then finally, NWelch does other things besides just the coherences and the nice power spectrum estimates. So you can detrend your time series or the segments of your time series, which reduces your leakage from zero frequency. You can taper, which reduces your spectral leakage from the hard edges. You can correct bias. You can calculate spectral window. You can calculate both analytical and bootstrap false alarm thresholds on your coherences. You can do a statistical test for periodicity, the Siegel's test. You can do a periodogram if just you want to compare with Loam-Scargill. It's actually based on the NFFT, but it's similar to Loam-Scargill. And then anything that you compute, you can also plot. And so that's it. Thank you.
Thank you so much, Sally. That sounds really awesome. Does anyone have any questions? We have time for maybe one or two quick questions. I see. Oh, thought I saw someone there for a second. Feel free to raise your hand, or you can just come off microphone. Just a quick one while we're waiting here. I think it was one slide ago. You were talking about the thresholds here, and I'm just not familiar with this. What do you mean by the bootstrap versus the analytical here?
Yeah, so with this coherence statistic, there is an analytical formula that you can use to calculate your false alarm thresholds just based on the number of data points in the time series. But you can also calculate it by bootstrap. And so the way to do that is you take both time series, you scramble them, and then you calculate the coherence between the scrambled versions, and you repeat that some number of times. So the default in NWelch is 10,000. And then you just construct percentiles from that, and that will give you your bootstrap false alarm thresholds. And the analytical is actually really good here. I mean, sometimes you're suspicious that your analytically calculated metrics actually hold for real data, but we've always found good matches.
That's awesome. Well, let's thank Sally. I'll just clap here alone in my office. But great talk. And if anyone has any other questions or discussions, please feel free to use the Slack, the Discuss Talks channel.